Welcome to the debate. Today, we are looking at something that feels, honestly, straight out of science fiction, but it is happening right now. It is the collision of artificial intelligence and our core biology.
Yeah, and we've been poring over the latest literature, and I have to say, the sheer volume of data being analyzed is staggering. I mean, AI is currently decoding petabytes of genetic and metabolic data every single day.
Right, we were talking about mapping the DNA of global bacterial populations, trying to untangle the human microbiome, which alone comprises roughly 39 trillion microbes, and tracking these really subtle proxy signals for insulin resistance.
And that last point on insulin resistance is critical context here. This is a metabolic crisis that is projected to threaten 540 million people globally by the year 2025. The stakes for getting this right are massive.
Today is strictly grounded in the recent literature analyzing these specific AI applications across bacterial genomics, human microbiota mapping, and metabolic disease prediction.
So, the central disagreement we are exploring is this. Does AI's unprecedented ability to recognize complex patterns in proxy data represent a robust standalone revolution that can finally bypass traditional, slow mechanistic biology?
Or, on the flip side, does relying on biased datasets and black box proxies introduce critical vulnerabilities that ultimately undermine the clinical reliability of these tools?
Right, and my position is that leaning heavily on AI proxies without a foundational mechanistic ground truth exposes us to dangerous systemic vulnerabilities, particularly due to severe data bias and environmental complexity.
And my position is that AI's multimodal pattern recognition definitively overcomes the bottlenecks of traditional biology, creating a highly accurate, entirely new predictive paradigm.
Well, I understand the appeal, but to establish why I am so cautious, we really have to look at how these models are actually built.
Let's look at the baseline reality first, though. Traditional biology is currently drowning in a data deluge while simultaneously being handcuffed by outdated, incredibly slow methodologies. I mean, in the microbial world, traditional lab culturing misses about 99% of bacterial species because they simply will not grow in a petri dish.
Well, sure, lab conditions are artificial.
Exactly. And in the metabolic space, look at how we measure insulin resistance.
You're referring to the hyperinsulinemic euglycemic clamp.
Right, the clamp. It is the gold standard. But let's be realistic about what that entails. It means hooking a patient up to intravenous lines, constantly infusing and monitoring their insulin and glucose levels for hours in a highly controlled lab setting. It is invasive, it's expensive, and it is completely impractical for the billions of people at risk globally. We cannot clamp the world.
No one is suggesting we perform a CLIMP test on 540 million people, but the precision of that test represents a biological ground truth.
But what AI allows us to do is derive that ground truth from the data we can collect at scale. The recent literature on next-generation sequencing is incredible here. We have deep learning models, specifically convolutional neural networks like Google's Deep Variant, that are sifting through raw genomic reads and distinguishing true genetic variants from random sequencing noise with 99.9% accuracy.
Deep Variant is an impressive piece of software, I will grant you that.
And it extends to metabolic health, too. Researchers are using sequence analyzing algorithms, specifically long short-term memory networks or LSTMs, to predict the Masuda index. That index is a direct mathematical proxy for the invasive glucose clamp we just talked about. And the AI is doing this using just 14 days of data from off-the-shelf continuous glucose monitors, achieving 88% accuracy. AI isn't just guessing, it is establishing a reliable, globally scalable ground truth based on patterns that human minds simply cannot process.
The predictive promise you are outlining sounds incredibly alluring. An 88% accuracy rate on a wearable device sounds like a massive win. But when you look closely at the literature, this predictive paradigm is essentially a house of cards built on fundamentally skewed data. We cannot conflate mathematical pattern matching with biological reality.
How is an 88% clinical correlation not reflecting biological reality?
Because the foundational data sets training these algorithms harbor severe systemic skews. Let's look at the bacterial databases right now. There is a massive 90% overrepresentation of gram-negative bacteria. If you train an algorithm on a database where 90% of the examples share a specific cell wall structure, that model is going to have massive blind spots when it encounters the rest of the microbial world.
Every dataset has limitations early on, but the sheer volume of data is actively correcting that.
It's not just microbes, though. Look at the metabolic models you just praised. The AI is predominantly trained on continuous glucose monitor data from Western populations. When you decouple your predictive models from a fundamental mechanistic understanding of diverse human populations, you invite dangerous edge case failures.
Give me a specific example of an edge case failure in the metabolic space.
Lean diabetics. AI algorithms heavily trained on Western phenotypes, where diabetes is strongly correlated with high body mass, consistently risk underdiagnosing lean diabetics. And that presentation is highly prevalent in Asian populations. The algorithm looks at the proxy data, sees a low BMI, and mathematically assumes low risk, entirely missing the actual biological distress.
But researchers are actively addressing those representation gaps using synthetic data generation.
You mean GANs? Generative adversarial networks?
Yes, they're using GANs to simulate underrepresented profiles, like African genomes, to balance the training models.
That is exactly the systemic vulnerability I am talking about. A GAN operates a bit like a deep fake generator, simulating a population's biology because you lack the actual empirical data is not the same as truly representing them. It's a synthetic approximation. If we deploy these algorithms without mechanistic validation, we risk generating an avalanche of false positives, causing massive patient stress, all while claiming we've mathematically solved global health disparities.
I see why you think that, but let me give you a different perspective. AI proxy models are not just adequate stand-ins for these traditional tests. They are demonstrably superior precisely because of their scale. You mentioned the risk of moving away from the clamp, but let's look at the 2024 Mayo Clinic study.
The one evaluating wearables across multiple continents?
Exactly. A massive study across the US, Europe, and Asia. It proved that AI matched the diagnostic power of the clinical glucose clamp using data from basic wearables. We are replacing an invasive, expensive clinical procedure with data from smartwatches people already have on their wrists. Plus, look at VertaHealth. They are using AI analysis on CGM data from 20,000 patients. And they aren't just predicting risk. They are successfully reversing insulin resistance in 60% of those patients through highly personalized dietary models generated by the AI. And in the infectious disease space, look at Carius. They are using plasma NGS, next-generation sequencing, to detect bloodstream infections in immunocompromised patients in mere hours.
I'm sorry, but I just don't buy that. Let me tell you why. Replacing mechanistic tests with proxy data creates dangerous diagnostic blind spots. You mentioned CGMs, but the literature shows these multimodal AI models are increasingly pulling from highly unconventional, unverified inputs. We have models in the current literature using voice analysis to detect stress. They operate on the premise that the pitch and stress in your vocal cords acts as a proxy for your cortisol levels, and that cortisol proxies your insulin resistance.
Wait, you're saying they're analyzing the pitch of someone's voice during a phone call to guess their blood sugar?
Yes, and it gets further removed from biology than that. We even see algorithms utilizing consumer shopping data to infer carbohydrate loads. This isn't biological mapping. This is a socioeconomic proxy masquerading as a biological diagnostic.
Using shopping habits as a metric is certainly an experimental edge case, not the standard of clinical care.
But it highlights the trajectory. When you rely on inferences stacked upon inferences, voice to cortisol, cortisol to insulin, the peril of false positives skyrockets. Telling a patient their algorithmically generated resistance index rose 5% because of their grocery receipts induces unnecessary medical anxiety. We already know that not all insulin resistance immediately requires pharmacological intervention, yet these predictive algorithms often push patients toward preemptive drugs, like GLP-1 agonists. AI algorithms risk amplifying disparities unless they use hybrid human-AI loops to constantly refine and clinically validate these diagnostic thresholds.
A doctor needs to look at the patient, not just the algorithmic score.
I completely agree that human oversight is crucial for an individual patient's treatment plan, but human oversight simply cannot scale to the level of planetary biological complexity that AI is currently deconvolving. The human mind cannot process an environment as chaotic and vast as a metagenome. This is where AI's analytical power becomes non-negotiable. The literature details the use of graph neural networks, or GNNs. Think of a GNN like a massive social network map, but mapping bacteria as the nodes and the metabolites they share as the connections.
And the MetaHit Consortium used this, correct?
Yes, in France. MetaHit utilized GNNs across 1,200 European metagenomes and successfully predicted gut dysbiosis in 90% of cases. We are modeling microscopic interactions and scaling that up to population levels, and it goes far beyond the human gut. Look at environmental AI. The Tara Oceans project applied AI to 100,000 marine samples to model the plastosphere, identifying the specific microbes evolving to degrade plastics in the Pacific gyres. We have AI tools like Kraken 2 achieving 95% precision on deeply unbalanced datasets, and transformer models like Metaflan resolving bacterial strains from Amazonian soils to Arctic permafrost. Traditional biology cannot parse these massive chaotic environments.
That's a compelling argument, but have you considered the limits of generalizability here? You are dealing with planetary-scale biological complexity. I mentioned the human microbiota contains 39 trillion microorganisms. When you add the variable of immense local dietary shifts, the complexity shatters these standardized models. An AI trained on those 1,200 European metagenomes struggles immensely to accurately parse the microbiome of a population subsisting on Indian curry versus one consuming Japanese sushi. The fundamental microbial baselines are entirely different.
But commercial platforms are already operating globally to map exactly that.
You're likely thinking of platforms like Viome, which uses RNA sequencing AI to predict personalized probiotic responses. Yes, they ship to over 100 countries, but the literature shows these commercial models are severely limited by the data they haven't seen yet. Biology is not static. Look at the agricultural AI applications. Researchers are using convolutional neural networks to analyze field sample DNA for tracking rice blast fungus in Vietnam. It's a brilliant, highly localized tool, but it is deeply vulnerable to novel environmental shifts. When a model encounters an unseen evolutionary mutation or a novel ecological interaction in the soil, its predictive certainty becomes a massive liability.
That's an interesting point, though I would frame it differently. The rapid global scaling of these tools is actually the strongest empirical proof of their inherent robustness. We aren't just deploying fragile models that break when someone changes their diet. We are deploying adaptive, highly effective systems that are succeeding right now across incredibly diverse populations. Look at the Beto app in India.
The diabetes tracker?
Right, but it's not just a basic tracker. It is currently serving 5 million diabetics. It fuses AI with phone cameras to analyze skin tone as a proxy for jaundice and combines that with basic blood metrics. Its algorithm is actively outperforming standard World Health Organization diagnostic criteria in these urban communities.
Outperforming WHO baselines in a localized context is great. But what about broad clinical integration?
We have that too. In Europe, the Predictin study spanned 10 countries. They utilized electronic health records from 1 million people to deploy hospital AI that flags prediabetes 2 years earlier than standard clinical care. They slashed disease progression by 25%. And for the clinical trust issue, the field is rapidly adopting explainable AI, or XII. Tools like Lyme actually open up the black box. Instead of just giving a doctor a mysterious risk score, the AI points to the exact reason. It tells the clinician, I flagged this patient specifically because their fasting insulin crossed 10 microunits per milliliter. We are scaling effectively and transparently.
I come at it from a different way. The transparency of a single diagnostic variable doesn't erase the macro-level issues. The global scaling you're celebrating carries enormous hidden costs and ethical minefields that the literature clearly warns us about. Let's start with the computational hunger of these architectures. Processing petabytes of genomic data requires exascale GPUs. This massive reliance on computing power forces labs in developing nations to depend entirely on foreign cloud platforms. For instance, labs relying on AWS Outpost in Indonesia. That creates a deep technological dependency where the biological data of a nation is inherently tethered to foreign corporate infrastructure.
Cloud computing is the backbone of all modern science. That isn't unique to biological AI.
But interoperability failures are a massive issue here. A predictive metabolic model trained heavily on the Epic software system in U.S. hospitals frequently stumbles when deployed on Cerner systems in Europe, simply because the underlying data architectures don't align perfectly. And let's look at the most severe systemic risk documented in the literature, the dual-use nature of genomic AI.
You're referring to foundation models.
Yes, take foundation models like Meta's ESM. These models pre-train on 2.5 million bacterial proteomes to predict protein functions for drug discovery. It's an incredible tool for finding new antibiotics. However, the exact same mathematical weights that optimize a protein for therapeutics can theoretically be inverted to optimize bacterial virulence. The AI optimization of bioweapons is a very real deployment hazard. Scaling these algorithms globally without strict compliance with biological weapons convention safeguards is profoundly dangerous.
We absolutely must enforce those technical guardrails, and researchers take the dual-use threat very seriously. But we cannot let the fear of potential security risks obscure the undeniable paradigm shift that is actively saving lives in the present. The ability to process these massive data sets is moving humanity from a state of reactive medicine to truly predictive, precise healthcare. The literature shows us life-saving applications at the very extremes of vulnerability right now. We have AI analyzing the maternal microbiome to predict and save infants from necrotizing enterocolitis in neonatal ICUs in Kenya. We have AI modeling wastewater epidemiology to track antimicrobial resistance genes spreading in the Hudson River in real time.
Wastewater tracking is undeniably one of the best use cases for this technology.
It is a global guardian. By illuminating our microbial and metabolic blueprints, AI is definitively solving the biological data deluge and providing the tools we need to face incoming global health crises.
I have never denied that these tools are incredibly powerful, but we must remain rigorously objective about the fact that they are currently flawed biological proxies. A correlation coefficient in a highly controlled trial does not erase the dataset skew of a model trained predominantly on gram-negative bacteria or Western metabolic profiles. And as we expand these datasets, we have to respect data sovereignty. Look at Australia's recent moratorium protecting the genetic data of indigenous microbes from foreign sequencing. That is a perfect example of the caution required. The data represents the biological heritage and privacy of vulnerable populations.
On that specific issue of data privacy and access, I believe we actually find a crucial point of convergence in the literature. Both the rapid advancement of the AI models and the protection of patient data are being solved simultaneously through federated learning architectures.
Yes, federated learning is a brilliant development. It is an essential, non-negotiable step forward. The literature highlights how Brazil's Fiocruz Institute is successfully pooling 50 million electronic health records across their SUS health system to predict metabolic risks without ever centralizing the raw data. The AI travels to the local hospital's data, learns from it, and leaves without taking the patient records.
Exactly. It completely neutralizes the privacy risk. And we see the exact same collaborative training happening across hospitals in Europe, operating strictly under GDPR guidelines.
I entirely agree on that front. And alongside federated learning, the aggressive expansion of truly representative global databases is paramount to fixing the dataset skews we've debated. Initiatives like the NCBI's RefSeq or the Global Microbiome Conservancy are actively training models on data from over 100 countries. We cannot rely on synthetic GAN data to fill our blind spots. We must do the hard empirical work of sequencing the globe equitably.
Which brings us to the staggering future potential of this field. As we look forward, the literature points toward quantum AI. Institutions like IBM are developing quantum frameworks that will soon be capable of simulating bacterial evolution and antibiotic resistance in a matter of minutes. By 2035,
We could see the routine deployment of pocket DNA sequencers paired with edge AI, actively monitoring and preventing pandemics preemptively. The capacity to decode our microbial and metabolic blueprints is accelerating at an unimaginable pace.
It is accelerating incredibly fast. And that is precisely why we must demand that our understanding of the underlying biology keeps pace with our predictive algorithms. There is a vast amount of complexity left to uncover. I strongly suggest that anyone listening continues exploring the source material we've discussed today to fully grasp the profound implications, both the immense clinical promises and the critical systemic vulnerabilities of this technology.
An excellent point to end on. We leave the ultimate conclusion up to you, our listeners, as you weigh the evidence from the literature. Thank you for joining us on this deep dive into the biological algorithm shaping our future. Goodbye.
Goodbye.